All right, welcome to the deep dive, everyone. Ready to get those neurons firing. Today, we're going deep on a paper that really laid the groundwork for where AI is going, specifically on-device AI.
Sounds exciting.
It is. It's a 2018 paper. Might feel like ancient history in AI time, but it's super relevant.
I can imagine things move so fast these days.
It's titled Empowering Edge Intelligence, a comprehensive survey on on-device AI models. Quite a mouthful.
Definitely sets the stage.
It does, by Wang and a whole team from a few universities: Hong Kong Baptist University, BNU, HKBU, United International College, and Beijing Normal University.
A global effort.
Exactly. And what they tackled was this whole shift towards processing AI, not in some giant data center, but right on your phone, your smartwatch, even little sensors in like industrial equipment.
So bringing the brains closer to the action.
Yes. And this wasn't just a cool idea. There were some serious drivers pushing this. Like, think about the explosion of the Internet of Things. Billions of devices collecting data.
Right. Sending all that to the cloud would be a nightmare.
It's exactly. Delays, bandwidth issues, privacy concerns on device. AI was and is the answer.
Makes total sense. So are we going to break down this paper, see what they got right, what's changed since?
Exactly. Our deep dive mission today is to pull out the core insights. Where was on-device AI back in 2018? What challenges did they see coming? And where did they think things were heading? Think of this like a cheat sheet to understanding a really crucial part of modern AI.
I like it. A cheat sheet for the future, basically.
Pretty much. And this paper was really broad, covering the basics, the potential uses across tons of fields: smartphones, of course, smart homes, even things like self-driving cars and medical devices. And importantly, they dug into the limitations of these little devices and the whole privacy angle.
Super relevant, especially today with all the data privacy discussions.
So true. They were early in seeing this move to the edge. They even cited a Gartner projection. By 2025, they said 75% of enterprise data would be made outside traditional data centers. That's huge. Cloud alone can't handle that.
Wow, yeah, that's a tidal wave of information.
It is. And that's where on-device AI shines. Real-time processing, so think like a medical device, instantly analyzing your heartbeat, no waiting for the cloud. Plus, it's more efficient, less reliance on shaky internet, and you're keeping your data closer to you.
All huge wins. But I'm guessing there were trade-offs too, fitting all that intelligence onto tiny devices.
Absolutely. The paper dives into that balancing act. Shrinking AI down means sometimes sacrificing a bit of accuracy or simplifying the models to make them work within those tight constraints. It's that constant tension, fitting powerful AI into tiny spaces without losing the smarts.
A puzzle with real-world consequences.
Exactly. So to understand why this paper was so important back then, let's rewind a bit. Just before 2018, machine learning had these mind-blowing breakthroughs. AlphaGo beating a Go champion, early versions of what would become things like ChatGPT.
Right, like AI was finally delivering on the hype.
Exactly. But then we hit reality. Deploying these massive models in real-world applications, well, it wasn't so simple. The paper mentions GPT-3 specifically. It was huge GE, 175 billion parameters needing 800 gigabytes of storage. Your phone would explode.
Yeah, my phone struggles to store all my cat pictures, let alone that.
Right. So we had the cloud for training these giants, but at the same time, the Internet of Things was exploding. Edge computing was becoming a thing. Our phones were getting more powerful. It all pointed to on-device AI as the natural next step.
Driven by both possibility and necessity.
Precisely. And this paper didn't appear in a vacuum. They cite a bunch of other research-efficient communication in edge systems, which makes sense. Some data still needs to move around. There was work on AI for specific things, like self-driving car networks, wireless networks getting smarter. It sounds like this paper was tying all these threads together.
A big picture view of on-device AI specifically.
Yeah, that was their aim. They saw those other surveys as valuable, but they wanted a more holistic approach. How do we make efficient AI models that live on devices working within all those edge limitations? And they focused on optimizing the data itself, the model, and the whole system.
A three-pronged attack. Love it. Okay, so what exactly did they mean by on-device AI? What kind of devices are we even talking about?
Yeah, let's break it down, starting with the edge devices themselves. It's way beyond just our phones. Right?
Oh yeah, way beyond. They pointed out this whole range from powerful servers at the edge of the network to tiny low-power sensors. Your phone, sure, but also drones, the brains in self-driving cars, robots on factory floors, smart home gadgets. The variety is crazy.
And they give concrete examples in the paper. NVIDIA's Jetson platform, great for robotics and computer vision. Then you've got the Google Coral Dev Board, super efficient for image recognition. And of course, the good old Raspberry Pi, everyone's favorite for DIY IoT projects.
The little engine that could.
Right. And these examples, plus others like AWS B-Plans, Intel stuff, show how different devices are made for different jobs. Balancing processing power, battery life, size. It's a whole ecosystem of specialized AI gadgets.
That's not one size fits all AI.
Not at all. And then you have the AI models themselves, the algorithms that chew on data and make decisions right there on the device.
Yeah.
And it's not just those huge complex models we hear about, right?
Nope. They pointed out it can be simple rule-based stuff or more intricate machine learning. And what's interesting, they saw this trend coming of smaller foundation models made specifically for edge devices. They even mentioned Gemma 2B and Llama 3.2 1B, making powerful AI more portable.
So taking the brains of those cloud giants and squeezing them down.
Exactly. Though those specific models came out later, they nailed the need and the research direction. The goal was always clear. Meaningful AI on devices, no cloud needed.
Smart devices indeed. Okay, so we have the devices, we have the models. How does it all work together? They talk about an on-device AI pipeline with 3 stages: data, model, and system. Let's start with data. What needs to happen to the raw stuff before an AI can use it?
Data preprocessing is key. It starts with collecting the raw data, sensor readings, images, whatever. But this raw stuff is usually messy. So first you got to filter it, get rid of errors, inconsistencies, that kind of thing. They call this cleaned data. They even mention fancy techniques like active label cleaning and ensemble methods, but admit those are tricky on limited devices.
Yeah, got to make sure the AI isn't learning from bad data. So what's next after cleaning?
Feature extraction, finding the most important bits of information, making the data smaller, easier to handle. They give examples in melanoma detection, anomaly detection, where it's super useful, but got to be careful not to oversimplify and lose crucial details.
Another balancing act. And then they mentioned data aggregation. What's that all about?
Aggregation is combining data from different sources. Think sensors in a factory. Each one gives you a little piece, but together they paint the full picture. They specifically talk about federated learning here, which is cool because it keeps the raw data private on each device, but learns from all of them combined. But they also warn if the aggregation itself is too heavy, it can slow things down.
Right, got to stay efficient. Last step in the data stage is quantization, right? Sounds like another efficiency trick.
It is. It's basically reducing the precision of the data. Instead of super detailed numbers, you use slightly less detailed ones. Saves space, speeds things up. They mention sparse projection as an example used in facial recognition. It's like highlighting the key parts of the data and ignoring the rest.
Smart. Okay, data prepped. What about the model development itself? What are the key stages there?
Well, first you train the model. That's where it learns from the data. Then there's model design, picking the right architecture, the layers, all the settings to get the best performance for the task. And then, super important for on-device AI, you've got model compression.
Compression seems to be the name of the game here. Why is it so vital for on-device AI?
Because these little devices have limited resources, remember? Compression is like packing for a trip with a tiny suitcase. You got to get rid of the non-essentials and squish everything down to make it fit.
Makes sense. Data ready, model built and squished. Last piece is system integration, right?
Right. This is making sure the model works smoothly with both the software and the hardware of the device. Software optimization means tweaking the code to run well on that specific platform. Hardware optimization makes sure the chips and stuff can handle the workload. And then, boom, you deploy model, ready for real-time action.
It's like a finely tuned machine. Every part has to work perfectly together. Okay, enough about the techie stuff.
Yeah.
What can we actually do with on-device AI? They talk about application scenarios, and it's not just about making our phones cooler.
Right. Oh no, it goes way beyond that. They start with IoT applications, which is huge. Smart homes that learn your habits, personalize everything. Imagine your house basically becoming your butler. They also mention environmental monitoring, using on-device AI to analyze data for better sustainability.
Oh, so like sensors keeping an eye on pollution levels or tracking energy usage.
Exactly. And industrial automation is another big one. Imagine AI predicting when a machine is about to break down, avoiding costly downtime, or optimizing factory processes for maximum efficiency.
That's smart manufacturing taken to a whole new level. And what about agriculture? Can on-device AI help farmers too?
Absolutely. Think sensors in the fields, analyzing soil, weather, all that. On-device AI could then tell farmers the best time to irrigate, saving water and boosting crops. Precision farming powered by AI.
Love it. Beyond the IoT world, they also talk about broader edge computing applications. What falls under that umbrella?
This is where real-time data crunching shines. Facial recognition for security, intelligent traffic systems that adjust traffic lights on the fly to reduce jams. In manufacturing, it can constantly monitor equipment for predictive maintenance. And in augmented reality and virtual reality, it makes the experience smoother and more immersive.
So basically making our world smarter and more responsive. And then there's self-driving cars. That seems like a perfect fit for on-device AI.
Oh, totally. Those cars are basically data gathering machines, cameras, radar, LiDAR, the whole works. On-device AI is crucial to process all that in real time, make split-second decisions, navigate safely. The paper even mentions research on navigating tricky roads without traditional maps, all thanks to on-device AI.
That's seriously impressive. Last area they touch on is healthcare, which feels both exciting and sensitive.
For sure. They mention wearable devices that can do things like analyze your heart rhythm right on your wrist, AI models helping develop new drugs faster. It could lead to faster diagnosis, more personalized treatment, better outcomes. But, of course, keeping your health data safe is paramount.
Absolutely. That's where the on-device aspect is key. So it's clear this tech has massive potential across so many fields. But the paper doesn't shy away from the challenges either, the technical challenges of making it all work. And it sounds like there are quite a few hurdles.
There are, and they lay them out really well. First up, the limited resources on these edge devices.
Right. Our phones and sensors are nowhere near as powerful as those server farms.
Exactly. Many AI models, especially deep learning ones, are resource hogs. They need a lot of power to train, even more to run and make predictions. The CPUs and GPUs in most edge devices just can't keep up with that. So that's where those optimization techniques we talked about come, shrinking the models, simplifying the math, even special AI chips.
And it's not just raw power. The complexity of the AI model itself matters too, right?
For sure. More complex model, more calculations, more time to get an answer. On a device, that delay can be a deal breaker. Imagine a voice assistant that takes ages to respond. Nobody wants that. So a lot of work goes into designing lightweight models like mobile nets or using techniques like neural architecture search to find efficient designs.
Making AI nimble and quick. Then there's storage and memory limitations. Even though phones have decent storage these days, it's still finite.
And those fancy AI models can be huge, tons of parameters, big file sizes. So again, compression is key. Pruning to get rid of unimportant parts, quantization to simplify the numbers. It's all about making the model fit.
And memory usage is a separate issue, right? It's not just storing the model, but actually loading it and the data into memory to do the calculations.
Yeah, if the RAM is too small, things slow down or crash. They talk about techniques like model de-escalation, where a smaller model learns from a bigger one using less memory, and incremental learning, updating the model with new data without keeping all the old stuff around.
Clever ways to stay lean. And then managing all that data gets even trickier when multiple users or apps are fighting for resources.
Oh yeah, that's a headache. The paper suggests distributing data and models across multiple devices or using edge caching, where you store frequently used stuff locally to avoid fetching it from the cloud all the time.
Makes sense. Another big challenge, especially for battery-powered devices, is energy consumption management.
Definitely. AI can be a power hog. So they talk about energy-efficient algorithms like finets that do more with less power. And also, the device itself needs to be smart about managing power, using AI to decide when to ramp up the processing and when to chill out.
Like a little AI power manager, making sure the battery lasts. And hardware can play a big role here too, right?
Huge role. They highlight things like TPUs and FPGAs, specialized chips designed for AI, way more efficient than general-purpose CPUs. And the paper talks about even co-designing the hardware and software together for maximum efficiency.
Really squeezing every drop of performance out of the hardware. Another challenge, especially in our mobile world, is communication bandwidth limitations.
Right. Even with 5G, sending lots of data back and forth can be slow and costly. So pre-processing data on the device becomes even more important, filtering, aggregating, compressing before sending it. And again, edge caching helps by keeping the data local. The more you can do on the device, the less you need to rely on that internet connection.
And then we get to the really big one, data privacy and security. Handling all this personal data on devices spread out everywhere raises serious concerns.
Totally. Edge devices can have very sensitive data, health info, location, even financial details. The paper talks about anonymization, trusted execution environments, fancy encryption methods, all designed to protect data during processing, storage, and transmission.
And with data privacy laws getting stricter, like GDPR, staying compliant is crucial.
Absolutely. Companies using on-device AI need to follow the rules, have clear data policies, and be transparent with users to build trust. And of course, these devices aren't immune to hackers and malware either. The paper mentions federated learning as a good approach because the raw data never leaves the device, just the learning insights. Plus, they talk about combining different security methods, both software and hardware, for a layered defense.
A multi-pronged approach to security. The last challenge they highlight is model transferability and adaptability. Taking a model trained in one environment, like a powerful server, and making it work on a tiny device is tricky.
All right, it's not plug and play. They talk about the challenges of cross-device model migration, needing smart ways to deploy and manage those models. Plus, edge devices live in the real world with changing conditions like temperature, light, unreliable internet. The AI needs to be tough and adaptable.
And ideally, it should also learn and improve over time, right?
Exactly. The paper talks about continuous learning, where the model adapts to new data and user needs, and also being able to move models between devices seamlessly to maintain quality of service. And when there are sudden spikes in demand, they need elastic scaling, basically being able to handle the extra load without breaking a sweat.
So many challenges, but also so much potential. That's what makes on-device AI so fascinating. And the paper then goes into detail about the solutions, the optimization, and implementation techniques. Let's start with data optimization. We touched on some of this before.
Right, but they go deeper here. It all comes back to that garbage in, garbage out idea. Good AI needs good data. So they stress the importance of data filtering, cleaning up the mess before feeding it to the AI. And they mention those more complex techniques again, active label cleaning, ensemble methods, but acknowledge they're harder to do on limited devices.
Making sure the AI isn't learning bad habits. Feature extraction is key too, right?
Crucial. Reducing the data to its essence makes the AI faster and more efficient. They give examples in melanoma and anomaly detection where it's super effective.
Data streamlining for AI. And federated learning is highlighted again, aggregating insights from many devices without compromising privacy. Plus, data quantization, shrinking the data size without losing too much information, making the data lean and mean. And they bring up edge computing frameworks like AWS Greengrass and Azure IoT Edge. What do those do for data optimization?
Those are like toolboxes for developers, giving them the infrastructure to process data locally. Less reliance on the cloud, faster results. They give an example of adaptive ROI compression, basically focusing on the most important parts of an image for faster object detection. But they also warn these frameworks can be complex to set up, especially for smaller teams.
Power tools for the AI builder. Okay, moving on to model optimization techniques. This seems like a really active area of research.
It is. There's so much happening here. They start with traditional ML compression methods, things like Q8KNN for doing fast searches and using special memory types for tree-based models. There's even an example of an efficient ECG classification system using random forests.
Ah, so those older machine learning methods can still be useful on devices.
Totally. But then they dive into the deep learning world, and that's where it gets really interesting. First up, parameter sharing, a clever way to shrink those massive models.
How does that work?
Instead of each part of the neural network having its own unique settings, you strategically reuse them across different parts. Saves space, speeds things up. They talk about using it in CNNs and RNNs, specific techniques like k-means clustering and t-bases. It can be tricky, sometimes affecting accuracy or making the model harder to understand, but it's proven successful in things like speech recognition and recommendation systems.
Reusing the good stuff. Next up, pruning, which sounds almost brutal.
It's like giving the model a haircut. You remove unimportant connections or even whole neurons, making it leaner and faster. They mention dynamic pruning, where you prune during training, and post-training pruning. And they talk about combining it with other techniques, like quantization for maximum effect.
Streamlining the AI's thinking process. And quantization is back again, this time specifically for deep learning models.
Right. It's still about lowering the precision of the numbers, but they discuss frameworks designed for specific types of networks, like capsule networks and spiking neural networks. And there's hardware-aware quantization, where you match the quantization to the hardware for maximum efficiency. They highlight Octo and HAQ as examples.
Tailoring the math to the machine. And then there's knowledge distillation, which sounds almost mystical.
It is kind of cool. Imagine a big, smart teacher model passing its knowledge to a smaller, more efficient student model. The teacher, trained on tons of data, distills its wisdom into something that can run on a tiny device. They talk about different variations, self-distillation, dynamic distillation, even cross-modal distillation. It's often combined with other methods to make the student even smaller and faster.
Like a Jedi Master training a Padawan. Then we have low-rank factorization, which sounds very mathy.
It is, but basically it's about approximating those big matrices of numbers in neural networks with smaller, less detailed ones. Save space without losing too much information. They mention SVD training and micronet as examples. Can be computationally heavy, though.
Efficient math for efficient AI. Then there's hardware-aware neural architecture search, which sounds like letting the AI design itself.
Kind of. It uses algorithms to search through tons of possible designs and find the best one for specific hardware constraints. Like, give me a model that runs super fast on this chip. They compare different frameworks and highlight some successful ones like Proxyless NAS, MobileNet v3, and OFFA. They even talk about using it in federated learning.
Auto design for the win. Last one for model optimization is energy-efficient model design.
This kind of brings everything together. Designing models from scratch to be lightweight and power-sipping. They mention MobileNets, ShuffleNet, SqueezeNet, EfficientNet, all using clever tricks to be efficient without sacrificing accuracy. And MobileVeet is another good example, combining different approaches.
It's like designing a race car. Every element focused on performance. Okay, enough about models. Let's talk about the system itself. The last implementation section focuses on system optimization techniques, both software and hardware.
On the software side, they break it down into on-device AI learning frameworks and on-device AI inference frameworks. Learning frameworks like TensorFlow Lite and PyTorch Mobile are all about training and managing models on devices.
So the tools to create and deploy the AI brains.
Exactly. And inference frameworks are about running those models efficiently. They have a huge table comparing different ones like Tensor, OpenVINO, NCNN, RMN, and the list goes on. Each one has its pros and cons depending on the hardware, what kind of optimizations you need, and so on.
A buffet of options for the AI developer. They even have a table showing how PyTorch Mobile performs on different phones, real-world benchmarks.
Yeah, that's super useful. Shows you how different hardware affects the speed and accuracy of the AI.
Now for the hardware side, the silicon brains that make all this possible.
This is where specialized chips shine. The paper talks about CPUs, GPUs, FPGAs, ASICs, and NPUs, each with its strengths and weaknesses for AI. They give examples like NVIDIA's Jetson GPUs, Ylinx's FPGAs, Google's Edge TPUs, Qualcomm's Hexagon NPUs. They have a whole table breaking it all down.
So many options, it's like picking the right engine for your AI car.
Exactly, and they go into detail about specific research projects using these chips. ReadAttack and NCPU for CPUs, SparkNet for FPGAs, EdgeBERT for ASICs, fluid batching and bit-systolic for NPUs. They even talk about hybrid approaches, using different chips for different tasks. They really cover the hardware landscape.
It's amazing how much is happening to make on-device AI faster and more efficient. The paper then wraps up with a look into the future development trends, where they think things are going.
Crystal ball time.
Exactly. First up, impact of emerging technologies. 5G and beyond, with their crazy speed and low latency, are going to be game changers for edge devices. Real-time data, seamless communication, unlocking new possibilities in smart transport, smart cities, all sorts of stuff.
The infrastructure for a truly connected world.
And they see edge computing itself continuing to grow, pushing more processing to the edge for faster decisions, less reliance on the cloud, more privacy.
A more distributed intelligence. And they also highlight foundation models, those massive pre-trained AI brains, as key for on-device AI. Fine-tuning them for specific tasks on devices could be a huge efficiency boost.
Like taking a super smart generalist AI and teaching it specific skills. They also predict advancements in the adaptability and intelligence of AI models. What does that mean in practice?
Think AI that learns and changes on the fly. Adaptive learning, where the model adjusts based on new data and user feedback, like your smart home learning your habits and preferences. And context awareness, where the AI understands your current situation and acts accordingly.
AI getting smarter and more personalized.
Yep.
And sustainability and green computing are key considerations for the future, too.
Absolutely. Making AI algorithms and hardware more energy efficient, sharing resources between the cloud and the edge, using AI to monitor and manage the environment, all crucial for a sustainable future.
AI for a healthier planet. And of course, they address the ethical and social implications, too, which is super important.
Yeah, no getting around those. They emphasize privacy and trust, building those privacy-preserving techniques right into the systems. Fairness and bias, making sure AI doesn't discriminate, are also crucial. And understanding the wider impact on jobs, education, how we interact with AI, all those things need careful consideration.
It's not just about the tech itself, but how we use it responsibly. And based on all their analysis, they give recommendations for future research, things they think need more attention.
Yeah, they push for more work on model compression and pruning, getting those models even smaller and more efficient. They also highlight co-designing hardware and software, those specialized AI chips working in perfect harmony with the algorithms. And of course, more research on data privacy and security, making those systems bulletproof. Plus, fairness and explainability, making sure AI is transparent and accountable. And finally, they encourage collaboration between different fields, AI researchers, hardware folks, ethicists, social scientists, all working together.
A holistic approach to AI development. And what about the bigger picture, the potential impact on society? They talk about impacts and prospects.
They're optimistic. They see on-device AI making our lives better through smart homes, personalized healthcare, and other cool services. They also think it'll revolutionize industries, leading to more efficiency and innovation. Ultimately, they believe on-device AI will make society smarter, while reminding us to prioritize sustainability and ethics along the way.
A hopeful vision of the future. And that brings us to the end of our deep dives. But we always like to leave you with something to think about. So given how fast on-device AI is progressing and how capable these smaller models are becoming, what unexpected changes might we see as truly intelligent devices become part of our everyday lives, making decisions, acting autonomously, all while keeping our data safe and close to us? It's a question worth pondering.
Lots to ponder indeed.
And a reminder, this deep dive is for entertainment purposes only. Thanks for joining us.
Thanks for having me.